So I want to talk a little bit about, just graphically to show this concept of energy saving. So imagine you have like a pulp mill that has so many, historically has so many tons per year, so many kilowatt hours per ton, and so there's so many kilowatt hours per year over time. We choose a start date and end date for some intervention. So something would have happened without that intervention, right? The kilowatt hours per time would have changed, done something. But if we do invest in something that's efficient, or that there's some condition that actually does happen going forward in time between the start date and the end date. And so efficiency is just the difference between those two conceptually. But the key thing is that blue line is always uncertain. It's very important to try and think very carefully about what would have happened without that subsidy, without that investment, without that corporate decision to do this or to do that to become more efficient. And just another example is that so using the example of a production, this is like a commodity production operation. The kilowatt hours per ton, just due to, this is kind of an engineering concept, any industrial facility, or even a house for that matter, will have kind of a baseline level of consumption, right? And so the more you increase output, your kind of unit energy consumption goes down naturally. Well, the whole idea in energy efficiency is that you're trying to reduce the energy consumed across the whole range of production, using an industrial facility as an example. So, the green would represent something that's efficient. The blue is not necessarily, some energy efficiency upgrade, although that could be debatable by some ways of thinking of it. So in general, we can have things that are, energy efficient, but don't actually conserve energy, right? They don't reduce energy over time for the system of interest, whether it's the whole globe, British Columbia, an industrial facility, our home, our car. So energy efficiency does not necessarily equal conservation, same for savings, and I guess mathematically you could say savings and efficiency are not necessarily equal. And common examples like electric baseboard heat. First law efficiency is about 100%. Second law efficiency is criticized for being the old chainsaw. Cutting butter with a chainsaw is an analogy I hear often about to illustrate the second law and heating with electric baseboard heat. There's tons of examples where something can be more efficient by first law, or us engineers, myself included, love our first law efficiency, but putting that into a system could be worse by economic measures easily. And so I mentioned this idea of causality and policy, so I want to highlight the Rivers to Card article to illustrate this. So what this shows is this is electric utility demand-side management cost effectiveness. So from a public investment point of view, how many dollars per kilowatt hour unit of energy, so not peak demand or anything, but energy, it was reduced. And so some reports from Manitoba, Ontario, BC, these would be the utility estimates, right? They're down in that 0 to 10 cents per kilowatt hour range. Some of the independent research here, ECO, Aramura, and others, Lofgren and Kulak, is who this one is, that's very, I've seen cited for here in BC. They're all in that, certainly the 0 to 20 cents range. And then we have the Descartes one that's up there, the Rivers one that's up there. They're optimistic or lower confidence interval that it's $2 a kilowatt hour. And ultimately, the central estimate is it just goes to infinity, the cost effectiveness, because you've got, you would be dividing by 0. So some mathematician might disagree, but you divide by 0 or a very small number, you approach a very big number, right? And so what I want to do, I had the benefit of some public health education as well, and I see, I really am a big fan of interdisciplinary studies and interdisciplinary thinking. So in the public health field, this Bradford-Gale criteria has been around for a couple decades at least, and they have a very nice systematic way of looking at the causality of health intervention, public health interventions, or the lack of, right? So I'll use like the Rivers to Card thing. Did those expenditures really cause a savings in kilowatt hour, or was there a lack of a causal connection between any of these things, right? You have no replication that I can find that shows that. It stands out. Alternative explanation. So why is Canada so different from the U.S.? In the article, it cites free ridership and rebound effects. I can talk more about those in question and answer, but there really needs to be an explanation. That really doesn't help us, in my opinion. Why would free riders and rebound effects make us so much worse? This is aggregate all of Canada, 16 years, than the U.S. that's been studied by, replicated by, multiple. And consistency with other knowledge, I could talk more. So a systems approach. So I think I'm looking at about 5 minutes. It's probably enough. So I like this article. We use this for teaching purposes at UBC. Energy systems are a couple human and natural systems. We extract sunlight, fossil fuels, and other things from our ecosystem, and we convert it into commercial energy forms that we use. There's methods for approaching systems that are described as coupled human and natural systems. Our energy systems are a human system. And why use a system approach? Because the whole idea is that, I was pleased to hear one of our new person has interdisciplinary studies, because the whole idea of interdisciplinary view of things is that we can find, basically reveal things that you wouldn't reveal separately. And what I like to use is this to describe energy systems as a system, the 6 building blocks approach, where really energy systems are designed in this way of thinking to deliver energy services. And then you back up and you have your service technologies, you have distribution systems, there's energy carriers, which are things like electricity, natural gas, steam. Then you go further back upstream in the system, you have transmission systems. This terminology certainly fits for electricity and natural gas. This transformer terminology would be like a gas processing plant. I'll go through an example. Then you have resource extraction and known reserves there, and there's always storage. We're matching the time domain. Our supplies never match exactly when we want to have our energy services. So all energy services, all energy systems always have storage somewhere, and probably multiple points. So I'm just going to talk about the terminology. The metered energy that we use, like for this facility, would be final energy. And that's important to know, like Statistics Canada, International Energy Agency, they'll report final energy statistics, they'll report primary energy statistics. That graph of quality of life I showed you, that was primary energy, right? It's important to know the difference, because obviously you have losses to get to that final point. And just to show quickly an example of hot water to illustrate this, the service is hot water. We might need it with a tankless hot water heater like I have. There's polyethylene distribution pipes. I'm pleased to be able to go visit Fortis, BC. I didn't realize it has some LNG storage to meet winter peak for natural gas. There's transmission systems, a lot of those in this province. This is a McMahon gas plant. It turns sour natural gas into sweet natural gas. And of course, you go further upstream, and a lot of that natural gas came from shale gas through hydrofracking. And there might be storage. Pretty much talked about that. So energy and behavior, and why behavior matters. So these rebound, in short, the rebound effect, the free ridership, the response to energy behavior is behavioral, right? So this article by Dietz is another kind of famous article. It talks about CO2 wedges from behavioral actions, and you could, with that article and others, this is just my reading of this, you can classify behaviors as either operation, maintenance, or purchasing. And I've spent a lot of time more on the industrial sector, and this is every bit as valid in an industrial facility as it is for our homes, which the examples are illustrating for homes. And this book and this McKenzie Moore Community-Based Social Marketing is a mandatory part of our demand-side efficiency course at UBC, and specifically because of the importance of behavior and how to change behavior systematically in ways that have been shown to be effective. Information campaigns have been shown to be not effective. Until a few years ago, I probably would have said, yeah, information campaigns and things will happen. Well, there's a lot of evidence that that does not work. the structured approaches have been shown to be effective. And I'll just conclude with a few quick examples. Lee Shipper studied a lot, amongst other things, transportation, another great mind that we lost this year, and he had this as-if model. This is the only reference where I send you to a YouTube. Go to YouTube and watch Lee's lecture on transportation energy. And so one of the things, like my own thesis, I studied diesel cars in Europe, and I can show you the figures if someone wants during questions. But diesel cars compared to gasoline, they're more energy efficient, they're more lower CO2 at the tailpipe, but guess what? In terms of the way people purchasing behavior and the way they drive them with rebound effects, Lee was one of the researchers who showed there's no attributable CO2 savings to that efficiency. Better first law efficiency, but at the end, no savings of CO2. This is another colleague at UBC, Professor Zariki, who's recently published with one of his students an article on household energy use. And I would call this is definitely just an example of a systems approach. I won't get into it, but you can see this is not just your standard engineering model, conversion, illumination out the other end, or heat or something, right? You've got behavior, habits, and attitudes and things built into this way of thinking. And then lastly, I'd like to highlight smart growth, something we're familiar with. I'm sure there's some land use transportation expertise in this room. That is a systems approach. And further to that, I like this Energy and Health article in The Lancet that shows, Elmer talked about, I'll conclude, building this bridge we have about half a lane of a highway, right? Well, we need to start thinking, in my opinion, bicycles. We need a 6-lane bicycle bridge, right, in our world of energy and green technology. Because I come from an engineering background and I studied cars for my thesis, you say, oh, what's the best car? I don't know, but I think it's the wrong question. What's the best way to get around, right? There's a lot of evidence, and land use transportation hits on this. The most efficient energy system is to power with food, and to those who can, and when, to the extent we can, walking and cycling. There's a lot of social connection. Obviously, the emissions are just a side benefit. There's a lot of human health, countering this, what's been called by the public health, the obesity epidemic, and the physical inactivity. So I'll close with that there are legitimate reasons why energy use is important. There's legitimate criticism of energy efficiency policies or the way it's carried out. No energy system is benign. I had the privilege of working like a year equivalent full-time on some solar thermal power in the high desert of California. I love it. I work on coal-fired power plants a lot. No energy system is benign. Everything has some impact. So my argument is until there is no truly benign, low cost by all arguments, and long-term resources. So we need to keep efficiency on the table. And that efficiency and conservation are plausible if we employ a system approach, sound science, and directly address it with policy. Thank you very much.